All right, so we're in section 1.2, modeling growth and decay. And the first problem, the first example says, a car depreciates as it gets older. Suppose that a particular car loses 1/5 of its value each year. Write a recursive formula to help you find the value of this car when it is 6 years old if it cost $23,999 when it was brand new. All right, so remember our recursive formula, first thing that we need is a starting value. So we have the first value here is $23,999. Remember, it doesn't really matter whether you use u sub 0 or u sub 1 for your recursive formula. You just still have to keep track of like what year you're on. Let's just use u sub 0, saying that's our starting value. And I think that'll actually be easier in this problem. So 23,999 will be our like 0th year, but our first value of the sequence. And so if we're going to figure out how much the car is when it's 6 years old, we need to be thinking about, okay, are we having a constant ratio here, in other words, a constant multiplier, or do we have a constant difference? All right, well, if it's 1/5 of its value every year, that means we're going to be having a constant multiplier. If we have 1/5 of its value being lost, then that leaves us with 4/5 that remains, or 0.8 that remains, or 80% of its value that remains after a year. So in other words, it loses 1/5 or 20% of its value, and it retains 80% of its value. So we're going to then use this right here, the 8/10, as our constant multiplier. Right? So we're going to have u sub n is equal to 0.8 times u sub n minus 1. And since we used 0 here, then we could say n is greater than or equal to 1. All right, so that is our recursive formula, and now we're actually going to need it to figure out, well, how much is the value after 6 years? Well, this is our starting amount, so after 1 year, it would be 80% of this, right here, 23,999. So if we took 23,909 times 0.8, that would give us, well, let's see, after year 1, at year 1 then it would be $19,199. If we then took that value and multiplied it times 0.8 again after year 2, it would be $15,359. And if we then took that once again and multiplied it times 0.8 after year 3, it'd be $12,287. And I'll kind of spare you the in-between work here. But once you did that, when you got up to the 6th year, you would end up with $6,291.19. All right, so you could use that 23,999 on your calculator, enter, times 8/10 times 0.8, enter, and then just count to the 6th year. And if you wanted to make an explicit formula, you certainly could. In this case, it'd be something like y equals our starting amount, 23,999, times our constant multiplier, 0.8 to the power of x. But we're just going to stick with our recursive formulas here, since that's what it's asking for. But if you're curious, that's what it would look like for an explicit. So this situation is now about decay. So it's basically exponential growth and exponential decay. So this is exponential decay. The common ratio, or the common multiplier, is 0.8. All right? And that represents a 20% decrease. Okay? As 1 would represent 100%. So then if we're taking 20% away from that, then that would leave us with 80%. And that would be equivalent here, if you want to think of this constant multiplier as more like 80 hundredths, that's equivalent to 80%. So that means that the percent change has gone down 20%. Okay. Example number 2, Gloria deposits $2,000 into a bank that pays 7% annual interest compounded annually. This means that the bank pays her 7% of her account balance as interest at the end of each year, and she leaves the original amount in the interest if she leaves the original amount in interest in the account. When will the account reach a balance of $3,000? All right, well, in this case, instead of decay, we're going to have some growth because interest, in this case, makes that $3,000 increase. Or sorry, the $2,000 increase, we're going to see when she gets up to $3,000. So we're going to have our beginning value, we'll call u sub 0 again, is 2,000. And now we have to figure out, okay, what's our common ratio? What's our growth factor here? Well, unlike the last problem, this problem, we're at 100%. And instead of subtracting a percent, we're actually growing by 7%. So 100% plus 7% would be 107%, which as a decimal would be 1.07. So this right here, 1.07, is going to be our constant multiplier. Think about it in the last problem again. We took 100% minus 20% to get 80% because it was decreasing, and then 0.80 was our constant multiplier. So 1.07 is our constant multiplier times u sub n minus 1. By the way, I know we could put this u sub n minus 1 first and then the 1.07 second. It's kind of your preference. And again, since this is the 0 here, and it's greater than or equal to 1, if we use our u sub 0 as the first term. Okay, so now let's go ahead and figure out how long does it take before we get to $3,000. Okay, so if we go ahead and punch in $2,000 as our original amount, after 1 year, we get up to 2,140. So year 1, $2,140. And then in year 2 will be $2,289.80. So about $2,290. And then we'll continue on with that until, so year 3 we're at 2,450, year 4 we're at 2,621, year 5 we're at 2,805, and finally at year 6 we are up to $3,001.46. All right, so when will the account reach a balance of $3,000? At year 6. All right, so unlike the last problem, this problem is all about growth, not decay. And the common ratio, therefore, is going to be bigger than 1 because it's going to make it grow. In this case, it was 1.07. And so the percent change, again, is how much was added, which was that 7%. So a 7% increase was our percent change. So basically the percent change is how much of a change from 100%. So in the last problem, it was down 20% to get us the ratio of 80% or 0.80. In this case, we're growing, so it goes up. And so 7% turns into 1.07 as a constant multiplier. Okay, but now what if Gloria's bank compounds the interest monthly instead of annually? Now when will her account reach a balance of $3,000? Okay, so this is where using a recursive formula gets a little bit tedious. And we start with the same idea. u sub 0 is equal to $2,000. And this time, though, if her interest rate, which, by the way, remember was 7%, 7% interest, is compounded monthly instead of annually. So before we took 100% plus 7%, but now we're going to take 100% plus 7% divided by 12 months. Okay? In other words, if we want to think of this, that's like 1 plus 0.07, so now I'm just changing these instead of from percent, so this is 100% up here, plus 7% divided by 12 months. So that would be equivalent to 1, and then 7% is equivalent to 0.07, 7/100ths, and divided by 12 months. So now this right here becomes our constant multiplier. Now if I try to change that into a decimal, I actually get a funky repeating decimal. 0.07 divided by 12 ends up being basically 1.00583 repeating. So for a constant multiplier, I mean, I suppose you could write this. It's going to be tricky to get that 0.3 repeating as a decimal if we're going to get up to $3,000 here. But let's just write it down. So we've got u sub n is equal to 1 plus 0.077% divided by 12 months. All right. And times the previous term. So times u sub n minus 1, where n is greater than or equal to 1. All right. Well, let's see if we can punch this into the calculator and do it recursively and figure out how many months. So remember, $2,000 is our original amount, and then we're going to multiply that times 1 plus 0.07 over 12. And so, for instance, we punch that in after 1 month. Now remember, we're talking about months here. So after 1 month, you are going to be at $2,011.67. After month 2, you're going to be at $2,023.40. Okay, so this is going up very slowly. In fact, if I keep pressing enter and keeping track, so that's 1 month, 2 months, 3 months, 4 months, 5 months, and so on and so forth, actually takes us up to 70 months before we finally get to $3,005. And so that is actually going to be our answer in this case. We have to, when we're using a recursive formula, really keep track of our counting. 1 month, 2 months, 3 months, 4 months, 5 months, and all the way up to 70 months before we cross over $3,000. So if we think about what 70 months is, okay, so that'd be 5 years. Okay, 5 years would be 60 months, 5 times 12, 60, and then another 10 months before we would get over $3,000. So you can see there's a little bit of a difference between that problem and the previous one. It's really at the previous problem in example number 2, when we're compounding annually, it took after 6 years. At least this way, when it's compounded monthly, you're getting it a little bit faster. It only takes 5 years, 10 months before you get to $3,000 as opposed to 6 years.